Okay, so in this question we have a proton moving with an initial speed of 2 times 10 to the 6 meters per second, and it's moving towards these series of parallel plates, and you can see the way they're drawn here. There's a tiny little hole in each of the first 3 plates to allow the proton to pass, and at the back the final plate is solid. The plates are charged, the first one being 0 volts, negative 15,000 volts, negative 30,000 volts, negative 40,000 volts. And what we want to calculate is how fast the proton strikes the final plate. Now for a question like this, we have a choice. We can use our kinematics and dynamics equations, or we can use our energy and our conservation of energy equations. And as I've already stated, with protons and electrons and things like that, where force fields can often vary, you're better off just using conservation of energy laws. So all we have to do is keep track of what kind of energy we've got, and then figure out whether or not it's going to be gaining or losing energy as a result of this plate configuration. So initially the proton is in motion, so it has kinetic energy, and then once it passes through this opening, it starts to experience an electric field generated by these parallel plates all the way to location C, which is our 40,000 volt plate. So let's start by labeling. We've got potential energy stored up between these plates, and the proton initially has kinetic energy. Okay, you can see I've labeled my initial kinetic energy as well as the formula. So the initial kinetic energy of the proton will be 1/2 mass of the proton times its velocity squared, and the velocity is given. It's going to travel between these plates, and we know now that the potential energy stored within the plates is given by Q times change in voltage. So the potential energy either gained or lost by the proton Q will depend on how much voltage it's passing through. So the next question is a question of logic. Rather than trying to sort out a specific equation, we're starting with kinetic energy. We're either going to gain or lose this much potential energy. Now if you look at the configuration, we know that a proton is positive. The second it passes through this hole, it's going to start to experience the electric field from all these plates. The plates continually get more and more negative as you move from left to right. So because opposites attract, it would stand to reason that this proton is going to gain speed. It's going to take this potential energy and add it to its initial kinetic energy to get a final kinetic energy that's bigger. In other words, it will make it all the way to the final plate. So let's put our proton at that location. I'll put it in gray. That'll be its final position, and label its final kinetic energy. I've drawn my vector, my velocity vector, to be a little longer, and that's the speed we're trying to figure out, its final velocity. Now it initially has kinetic energy, and we're going to add to it the additional potential energy it gains while it accelerates across the plates. In the end, when it smashes into this final plate on the right, it will no longer have the potential to be drawn to any more plates, because this is the last one. So all it will have at the end is kinetic energy just before it strikes the plate. So according to our work energy principle, our initial kinetic energy plus the change in potential energy as it accelerates between the plates gives us our final kinetic energy. So it's just a matter of substituting in the correct numbers. I use my formula sheet to find the mass of a proton, 1.67 times 10 to the negative 27 kilograms. The speed, the initial speed of the proton is given. The charge of a proton is the same as the charge of an electron except positive. It's called the elementary charge, 1.6 times 10 to the negative 19 coulombs. And we already know that it's going to pass through 40,000 volts. Notice I did not put negative 40,000 in here because we want its overall kinetic energy to increase. If I put negative in there, it's going to decrease. So I got to make sure it makes sense with my logic. And then set that equal to 1/2 mv final squared and solve for v final as follows. So we see that our final velocity when all is said and done is 3.4 times 10 to the 6 meters per second for our proton once it strikes the negative 40,000 volt plate.